So moving into chapter 18, now we're going to start dealing with our sampling distribution models. Specifically, what we're talking about is when we deal with the different models, we need to have some information. We have to understand what ways that we're dealing with so we can use this information to investigate our population. In order to do that, we have to understand what the models are doing. So something to remember is that in our ideal world, what we'd have is that our population, we'd investigate our population and we'd get a parameter about our population. Remember that a parameter is a summary statistic, is a numerical summary about our population. Now, we can't always do this. For one thing, it can be very difficult to simply gather information about the entire population. In some ways, we could say that it's effectively impossible. If I wanted to say something was true about human beings, I would have to investigate each and every human being in order to get that parameter about the population. I mean, it's simply not feasible. I can't do that, and I cannot actually know that I've found everyone. So instead, we have another route we can take. There's other things we can do. So I know I have some population out there. I can sample that population. And then from that sample, I can draw a statistic. I can get my numerical summary about my sample. I can use that statistic to make an inference and draw my parameters about the population in general. So our parameter is just that. It's a number related to a population. Specifically, I've called it that numerical summary about the population. Our statistic, a number related to the sample, a numerical summary of the sample, of some variable about the sample. So let's look at what these are. We have different indicators we're going to use for these. So I'm talking about the mean. So this is something I'm going to measure and find the average of something. When I'm dealing with a statistic, when I'm dealing with the sample, it's going to be X bar or it's going to be Y bar. When I'm dealing with a parameter, that's my mean for the population, it's going to be given by mu. When I'm dealing with the standard deviation, if it's a standard deviation about statistic, it's going to be the capital letter S. I'm dealing with the parameter, so now I'm talking about the whole population. It's given by the Greek Greek sigma. When I'm dealing with statistic, a proportion is going to be p hat. And of course, for the population, it's just going to be p. Now, will all samples of the same size give us the same statistics? Let's think about that for a moment. So let's say I have my population, and I'm talking about my population of students, and I take a sample of 5 of their test scores and find the mean test score. So does it make sense that if I pull a random sample of 5, I get a mean test score, and then I take another random sample of 5, which may include some of the same people, may not, am I guaranteed to get the same mean? And of course, no, I'm not guaranteed to have that happen. So we're going to have some sampling variability or sampling error. This is just the difference in values from sample statistics. And it's why we consider sample statistics to be a random variable. They're not all going to have the same value. They're going to fluctuate. In fact, sampling error is just that. It's the fact that some of my values are going to change from sample to sample. Now, my sampling distribution of a statistic, when you think about that, we've talked about this a little bit before, but let's talk a little bit more about it. So this is it's the distribution of values of a statistic taken from all possible samples of a specific size. And remember, we really spoke about this when we were talking about the Central Limit Theorem. This came up. So let's go over this example. In fact, I think this may end up being the Central Limit Theorem by accident. Okay, so let's consider we have a population that has 3 elements in it. There are only 3 elements in this population. Okay, so I'm saying element number 1 is just the number 1. 2 is the number 2. 3 is the number 3. There are 3 elements in my population. Well, if I take the mean of this, the mean of the population, 1 plus 2 plus 3, well, that gives me 6. I divide it by 3. The mean is 2. If I go and I calculate the standard deviation, I'm going to find the standard deviation of this population is 0.81649, etc., etc. And the variance, or the square of the standard deviation, 0.6 repeating. All of these values are parameters because they come from the population. Now, if I was to think about this differently, these are all of the possible samples I can make of size 2 out of this. So this is with replacement. Might want to notice, oh, let's go back into that. Now this is with replacement. So I pulled an element out, I might investigate it, put it back in, and then I pull again. With replacement, there's only 9 possible samples out of this. So this is what every single one of those would look like. They'd all have their own. Each of the samples could be 1 and 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. These are all of them. My mean of each sample, my x bars, 1, 1.5, etc., etc. My sample variance, so my s squared, for all of those different samples, for sample 1, 2, 3, etc. And of course, my standard deviations for each sample. Well, if I take the average, if I take the mean of each of these, I find the mean of all of my different samples comes out to be 2.0. I find my mean variance of all my different samples comes out to be 0.6 repeating. So my mean variance, my mean is the same as it is for the population. But if I take my mean sample standard deviation, this is not the same as what I had for the population. If you remember, for the population, this was actually let's see here, we'll try this again. If you remember right, for our population, it was actually 0.81649. Now we kept having more digits coming off. So that if I take the average, I'm going to get my mean value, I'm going to get the variance, but I'm not guaranteed to get the standard deviation back out of it from the average of all my standard deviations. And if I looked at my histogram of all my different ones, I find that's nice little normal, my distribution of the means. If we look at all these different means, if I plot them as a histogram, this is what I get. My minimum value is 2, maximum 2.5. This is what I end up with. So what we're seeing is that the mean of the sampling distribution model means, so the mean of the means is the mean of the population. And this is where you might hear me say, the mean is the mean is the mean. The mean of the sampling distribution means is the mean of the population. So this means that a sample mean is an unbiased estimator. Next, we find out the mean of the sampling model variances is also equal to the variance of the population. So a sample variance is an unbiased estimator. However, a sample standard deviation is not an unbiased estimator. The average of the standard deviations is not the same as the population standard deviation. So distribution of sample standard deviations doesn't hone in, it doesn't center around the population standard deviations. But with these first 2 pieces of information, there's some stuff I can do. So, I'm sorry, unbiased estimator can fall, it can be outside the true value, but the distribution of those estimators will match up to a normal distribution in certain cases. So, if we can check these assumptions we're going to make, we see that our distribution, we saw that in our first little histogram. So I'll go back to it. We saw in our histogram this was approximately normal. And in fact, it is approximately normal. It does become normal when certain conditions are met. And if that's true, the normal model gives us some very powerful tools we can use to evaluate our statistics. But we have to go over our assumptions. We are making a couple of assumptions when we do this. First of all, we're assuming independence. Okay, this is an assumption. In order to prove this assumption, we need to check some conditions. So we want our values to be independent. That's what I said, the sampled values must be independent. It's hard to be sure that this is true. We can't really know this, but we can check some conditions. And if we meet them, it'll be good enough. First one is randomization. Were the data values sampled randomly? And that's what I've been saying. We want that in our surveys, we want our experiments, we want our studies. We want it here too. Second one, 10%. Sample size, N, is less than 10% of the population. And the second way is the way you're going to communicate this. So when we're taking exams, if you want to communicate to me that this has happened, you'll just do 10 times, and let's say my sample size was 50. And is that less than, and let's say this was people, so 10 times 50, that's far less than if we're doing the population of the US, is my population. Then it's 10 times 50 less than the population of the United States. Yes, it is. Far less. It's 500. It's far less than 307 million. Right. Large enough. This is our next condition that we have to have met. So we've met our randomization. We've met our 10%. We need to have a large enough sample. So if the original population is normal, the sample can be small. If we start with something that's normal, we're going to end up with something that's normal. However, our original data may not have been normal. So if our original data isn't normal, we're going to need a large enough sample to deal with. The closer our sample is to being normal or uniform, the smaller our sample can be. Generally speaking, it's a rule of thumb. This isn't a hard and fast rule. There is no like perfect rule in statistics for this. We state that if n is larger than 30, we generally say this is large enough for the central limit theorem to start to kick in. Now, what is the central limit theorem? Okay, the central limit theorem is it's a rule in statistics, and really, if it wasn't, to say this is the fundamental theorem of statistics is not to overstate it. If it was not for the central limit theorem, there'd be no statistics. Statistics relies on this as it's called the fundamental theorem for a reason. It's fundamental. So central limit says that the mean of a random sample has a sampling distribution whose shape can be approximated by a normal model. The larger the sample, the better the approximation. Now, what we did to work on this, we did an exercise in class. You'd have to continue it. So we investigated some dice who worked as groups to do this. It's a central limit theorem worksheet, and I've already uploaded to a classroom, but you should have already completed this. So what we found is that central limit theorem did apply, and you can go to this website. I'll actually go to it so you can see it. So you can see how central limit theorem works. And this is what we see. So we have a simulation here. It's onlinestatbook.com/stat_sim sampling_dist. We click begin. And what we're doing is we have in this first one our parent population. Now we can change this. We can change what our population looks like. So we don't want it to be normal. In fact, I want it to look very unnormal. We played around with this in class. We see off on the side, it gives me a mean and a median and a standard deviation. I find all my summary statistics about. I can look at skew. We haven't talked about kurtosis, but we can see this is definitely not normal. Now I can go in and say, well, give me a sample. And I want to know the mean. We're going to do a sample size of 5, and let me do that 5 times. If I do this, I find some values. I have a mean of 18.45, a median of 19. Well, the median actually came out to be just like it was in the parent population, but my mean is a little off. But what if I did 5 more? Now I'm 18.43, and I can keep doing this, but let's go ahead and see. If I did this long enough, what's going to happen? So right now I've done 70 of these. Well, let's say I've done 10,000. Whoa, I'm getting pretty close. Well, do another 10,000. We're looking at this distribution. This is really turning into a nice normal model. Now, my mean is now almost exactly right after having done this repeatedly. And if I do this long enough over time, the way the mathematical proof works out, and here we happen to hit it. It took us a little while, but we got there. Our standard deviation is definitely different, but our mean is right about where it needs to be. Our median is right where it needs to be. So, well, let's clear that out. Let's say we did a different one. Let's say we did a sample size of 16. We pulled 5. Well, again, our median's off, our mean is off, but I pull another 5. Oh, we're getting closer a little bit faster now, even though we haven't pulled as many. Right now, we're only up to 65. 70, we're at 19, and 19 for median. So we're actually getting pretty close. But if I pull 10,000, we actually end up with just 10,000, we've almost matched. If I do another 10,000, it looks like we're going to hit it really fast, much faster than we did before. But we notice again, our standard deviation again now is much smaller again. So let's try going ahead and jump up one more time to a sample size of 25. If I pull 5, well, now my median's a little high, my mean's a little high, but pull another 5. We see already that central peak is growing. I pull our first 10,000. And in just the first 10,000, our median is already right where it needs to be. But again, our standard deviation, in fact, it's not just smaller than its population, it's even smaller than the previous sample sizes. And we can do animated. This is just if we pulled individual samples to get a sample size. Okay. Go a little faster, faster still. And we can see where the sample is going to build into it. If we're just doing random samples, this was going to happen. And that gave us 25. My first sample came through. Of course, this would take a while to show this way. That's why we don't do it. Okay. Last one, fit normal, is just so we can see what's happening. So we pull 10,000, then fit normal so we can see that graph. Do 100,000. It's really not significant changes happening at this point. Now, there's some minor changes, but doing 100,000, there's 800,000, 900,000, 1 million samples of size 25. Again, our mean is pretty fixed at this point. Our median is right where it needed to be. This is the central limit theorem in action. And this is what we saw when we did the dice rolling activity in class. So that is how the central limit theorem works. No matter what my original data might look like, we can clear this out. See if we can give a nice reset here. Let's see if I can reset it. There we go. Now, if we started off with a nice normal distribution, well, let's pull in 5. And let's do sample size 10 this time. Okay, our mean is 16, but our new mean is 16.6. So let's just do a few of these. Oh, okay, good. We didn't get the 10,000. Wanted to avoid that. Let's just pull in that we did the distribution of 100 repetitions. One too many. So if we did a sample of size 10 100 times, this is a distribution, a histogram of those distributions, of those means. Now if I had done 10,000, well, we instantly, with 10,000, jumped right away to our 16 and 16. But here we only need a sample size of 10 to do it. The more normal your data, the faster it happens. So we can try for a uniform distribution. Everything has the same probability. We pull in 10,000, sample size of 10 again. And already, we're not quite exactly right. We're a little off. But this is the difference between a uniform compared to starting out with normality. We didn't start off with normality this time. We start off with uniform. So we need a little bit more work for it to happen. And just, this is the central limit theorem, how it operates. So that gives us a really powerful tool for dealing with this. So you can play around that website a little bit more if you want to. Go there, play around, change the distribution, see it for yourself. So what it's saying is that if we do a random sample from a population, the population has some mean, and we call it mu. And it has some standard deviation, we call it sigma. The sample mean is going to be, that's x bar, is the same mean as mu. But the standard deviation changes. And we saw that. We saw that in those samples, the standard deviation of the distribution of the means was less than the standard deviation of the population. And that's what we get with our formula. Now, other than that, it's the same. So our normal distribution, we can summarize it. We can say it's the normal model with a mean of mu and a standard deviation given by the sigma divided by square root of our sample size. So let's think about this. Let's say we're dealing with SAT scores. When we say SATs have a mean of 500 and a standard deviation of 100, then what about the mean of a random sample of 20 students? What would that be? So if we think about this, we're interested in the distribution of possible means from samples of SAT scores. So if SAT scores have a mean of 500, standard deviation of 100, the SAT is normalized, it's reasonable to assume that the model for all SAT scores is normal. Remember, if we start with normality, we're going to keep our normality. If we started normal, we're going to end out being normal. But before we do any work, we need to list our assumptions and check our conditions. In this case, remember, we want to talk about independence. Is it reasonable to think SAT scores of 20 randomly sampled students are independent? Yeah, that's reasonable, as long as the students weren't all from the same school, because we know schools tend to have clusters of SAT scores. So that's our assumption. Our independent assumption, yeah, they're probably independent. Randomization, it did say that 20 students were sampled randomly, and then our 10%. 20 students, yeah, that's less than 10% of all students, because 10 times 20, well, that's less than the population of all students. So our next assumption was big enough. Is it big enough? When we think about that, our condition, the histogram population is unimodal, roughly symmetric. And we kind of got that. As we were talking about the central limit theorem, if they give, by the way, if I have a graph, it's easy to see. But if I don't, sometimes the information is given to me. In this case, they didn't say it, although they kind of did, because they said it's SAT scores. And about SAT scores, they're standardized. So we know there's some normality to them. But they don't, well, as the sample size increases, as it increases, the central limit theorem has time to kick in and make the distribution approximately normal. 20 students may not be a large sample by itself, but since it's a standardized test, there's already that normal distribution to the model. It's designed to have that unimodal peak right there in the middle. So under these, we can say the distribution of the samples is going to follow this. So we end up with a standard deviation is going to be equal to sigma divided by square root of n, or 100 divided by square root of 20, and that gets us about 22.36. Now, of course, you want to show the rest of your answer, so draw it. What would that distribution look like? Well, it's going to be a normal model, mean of 500, and then I'm going to find my standard deviations and move outward so I have 3 of them. And I have listed 68, 95, and 99.7. I could put this in words if I had to. 68% of samples of 20 students' SAT scores will have a mean between 477.6, and let's just, so we can all see what we're talking about here. Kind of a little odd there. Try that again. It will have 68% of the time, we'll have between 477.6 and 522.4 as their mean. 95% of the time, a sample of 20 randomly chosen students will have a mean SAT score between 455.3 and 544.7. And 99.7% of the time, my sample mean of 20 students will be between 432.9 and 567.1. That's exactly what we just did. Do our tell. So we did this show, we draw the picture, then we do our tell in order to finish it. So let's try another one. Let's say speeds of cars on a highway have a mean of 52 miles an hour and a standard deviation of 6 miles an hour and are likely to be skewed to the right. There's very few people who are driving very fast. So what we're saying is most drivers, and we'll draw this just so we have something to look at, most drivers are doing a regular speed, but some drivers are speeding a bit too quickly. So we're skewed to the right. So what could we see in a random sample of 50 cars? Let's think about that. Well, we want to talk about the distribution of the possible means from samples of speeds of 50 cars on the highway. We know on the highway the mean is 52 miles an hour, standard deviation is 6, but it's skewed to the right. So before we do anything, we want to think about our assumptions. We want to think about our independence assumption. Is it reasonable to think the speeds of the 50 randomly sampled cars will be independent? Well, if they're random, that makes sense. They're random, and it's 10%. 50 cars represent far less than 10% of all cars on the road, because 10 times 50 is far less than all cars. So our independence assumption seems to be valid. But our next one is big enough. Now, remember, our distribution is skewed, but a sample size of 50 cars is large. Under that, the central limit theorem is going to kick in and give us a normal distribution of those. So we're going to find a mean of 52 miles an hour. Remember, our standard deviation of the mean is the standard deviation of all the cars divided by the square root of our sample size. So in our distribution of sample means, we end up with a different graph. We won't have the original graph. There are those differences. Now, again, the big takeaway at this point is to remember what we're dealing with is not a distribution of the population. We're dealing with a distribution of samples from the population. Now, this is a fine point. These standard deviations have to change, but the mean won't. Now, last thing is, if I had to describe this distribution, I look at this distribution. I have this graph. It's nice. I've spent time on it. I've marked my mean and my standard deviations and what each one is. Well, I have 68%. 68% of the time, I'm fall within one standard deviation of the mean. So, in samples of 50 randomly chosen cars, 68% of the time, I'm going to find a mean speed between 51.2 miles an hour and 52.9 miles an hour. 95% of the time, I'm going to find a mean speed between 50.3 to 53.7 miles an hour. And 99.7% of the time, I'm going to find a mean speed of the sample to be between 49.5 and 54.6 miles per hour. That's just the last thing. We want to tell that. 68% of samples of 50 cars. Remember, this isn't 68% of the cars that I sample. It's 58% of samples composed of 50 cars. And that's like we talked about. If I sample people's grades, the outliers tend to be pulled back into the center by what most people are getting on the test. Same thing with this. Most of the speeds are going to start to be pulled away from the extremes. Of the guy who's doing 2 miles an hour on the highway, his dad's going to start to be pulled up by the other 49 cars in my sample. And the one person who's out there going far too quickly, their excessive speed is going to be brought back down towards the mean by the people who are doing a more moderate speed as they drive. So if we try this, at birth, babies weigh an average of 7.8 pounds, standard deviation 2.1. A random sample of 34 babies born to mothers living near a large factory that could be polluting the air and water shows a mean birth weight of only 7.2. Is this unusually low? This is different than the last question. The last question has just been describe the distribution. We want to know is something happening that makes something unusual. It's that word, that unusually low. Well, I know unusual means it has to be a less than 5% chance or 2 standard deviations away from the mean. Okay, so it can be plus or minus. So away from the mean, 2 standard deviations. But in this, I'm doing with samples. I'm not asking about one baby that weighs 7.2, but a sample. So let's first think about this. We're talking about the probability that a sample would end up that low. So remember, a sample is a sample is a sample. Now we do know, model for birth weights, it's probably unimodal. Most babies are probably in a certain thing. That makes sense that we'll have multimodal. And it may be normal. It will at least probably be kind of symmetric. You know, if I have a few really underweight babies, I'm probably only having a few excessively overweight babies. Now I've got to think my assumptions. Independence. Does it make sense? Is it plausible that my babies are independent in weight? Yeah, it probably is. 34 randomly selected babies. Oh, one baby's weight probably isn't affecting another in this case. My other assumption, I want to make sure they've been randomly sampled. And it said 34 babies were randomly selected. And 10%. Well, as long as there's more than 340 babies born to mothers in that vicinity, 34 is less than 10%. So big enough. Well, the model for all babies is unimodal. It's probably symmetric. Central limit theorem is definitely going to apply. And the sample size, 34 babies. And we said, that's not a hard and fast rule, but above 30, that's large enough. So under these conditions, the sampling distribution of the bar of X bar has the normal model. We can use a normal model. The mean is 7.8 and a standard deviation of, go ahead, try it. You have the standard deviation of the model divided by the square root of sample size, and we get 0.36 pounds. Well, if we work with that, now we can do showing what we're looking for. We want to find out, is this going to be an unusual event? So I can do this by finding z-scores. 7.2 is what I'm looking for. The mean is 7.8 divided by my standard deviation of 0.36. My z-score is 1.67. So how likely is that? Well, It's only 4.7%. That's less than 5%. So according to our model, it's only 4.7% of samples of this size are expected to have a birth weight that low. Because of that, it does appear that this is an unusually low result. This is something. Now, it doesn't tell me why the baby's underweight, but it just gives an idea that, yeah, this is an unusual result. Now, we've dealt with sample means. So part 1 is over. So we've talked about average weights. We talked about average weight, average time people have waited in line to get gas. All these different means that could have come up. Average birth weight, average grades, all those. Now we have sample proportions. So now we're not going to be talking about a numerical summary that we get where we have these values and we average them out, but proportion. How many people might say yes to a question? Now, let's think about that. We could have a simple random of 1,000 people from a population. X is the number of people in that sample who are Republicans. Well, there's 1,001 different possible values for that. It could be anywhere from 0 all the way up to 1,000 of them, or 1,001 possible answers. So what we do is we use p hat is going to represent the possible sample proportions. And it could be any of these values. It could be 0, 1 out of 1,000, 2 out of 1,000. We're going to get those different samples. But let's say we found in our sample 56% said they're Republicans. If I ran it again, maybe it'd only be 52%. Okay? Anytime we choose a simple random sample and calculate the p-hat for each sample, we could get a different one. But we still expect the distribution of p-hats to be approximately normal. But again, in order to do this, there's some assumptions we have to make. Now remember, we're dealing with proportions at this point. Some of our conditions are going to be a little different. But the first thing is we still have our assumptions. We still assume that our values are independent of each other, that what I found from one sample and what I found from one individual is not affecting another one inside of it. The other one is my sample size has to be large enough. This is going to be a little bit different. So remember, with proportions, here's my conditions. So I have my 2 assumptions, and now we have our conditions. 1, was the data obtained randomly? 2, 10%. Did I sample less than 10% of the population? Because once I go over that 10%, I no longer have my independence. And 3, this is for my sample size being large enough. I have to have my success failure. My sample has to have been big enough that I could have at least 10 successes and 10 failures. So n times p has to be greater than 10, and n times q has to be greater than 10. Now, on a test, you cannot simply say np is greater than 10. Show me what NP actually was. So let's say we took that simple random sample, size n, large population, that has some population proportion, some characteristic we're interested in. And if p hat is a sample or proportion of the sample having that characteristic, well, the sampling distribution of p hat is approximately normal. The mean of the sampling distribution is p. That means p is an unbiased estimator, just like the mean. But the standard deviation is a little bit different. Standard deviation for a distribution of sample proportions, square root of p times q divided by n. So, in our quick notation here, this is a normal model. The normal model for the distribution of sample proportions is the population proportion, and then its standard deviation is p times q divided by n square rooted. So, for example, let's say we're talking about the Census Bureau. They tell us that 40% of the 50,000 households in a particular area have more than one color TV in their household. What is the probability that a simple random sample of size 100 will indicate 45% or more households with more than one color TV when the population proportion is 40%? So we're trying to say, what's the chance that 45% or more of the households will say they have more than one color TV given that our population proportion is 40%? So there's a couple things we need to track for this. We need our P, we need our N, we need our P hat. And they told us P was 40, our N was their sample size, that's 100, and our P hat is 45. So let's check our conditions in order to support our assumptions. We need randomization, we need 10%, we need success failure. So was our sample taken randomly? Yeah, sample was taken randomly, 10%. 100, yeah, that's a lot less than 10% of 50,000, and I show that by putting 10 times 100 is less than 50,000. And then, of course, success failure. This is a proportion we have to do of success failure. Specifically, NP has to be greater than 10, and NQ has to be greater than 10. Well, 100 times 0.4, that tells me 40. I expect 40 people to say yes. 100 times 0.6, or my Q, is 60. I expect 60 people to say no. So we do have a big enough sample. We take care of that condition. Our assumption condition has been met. So let's see how we can model it. We can say that our normal distribution is given by the 0.4 for our proportion, and our standard deviation is the square root of 0.4 times Q, or 1 minus 0.4, all divided by 100. And we work this out, do a little bit of algebra. Our normal is going to be 0.4 and 0.049 for our standard deviation. Now we want to find out what's the probability of our p hat being greater than or equal to 0.45. That's what we said, 45% or more. So we find our z-score, p hat minus p divided by our standard deviation. That's going to be 0.45 minus 0.4. That gives us a z-score of 1.02. Let's put these in a calculator, find them. Now we put this into our calculator, and we want to find, and we draw in shade. And I honestly do recommend doing the drawing and shading. It's a highly effective tool. It's not just used by me. It's not just used while you're in stats class. There's statisticians who use this still. Before they go and make any claims about something, they still draw and sketch a curve just because it helps. So I'm looking for, from z-scores of 1.02 all the way up to 1E99s, all the way up to the end of it. And if I do this, I find an area of 0.153. Or our normal CDF, we use this, we find an area of 0.153. So that tells me there's about a 15% chance a sample size 100 would have a proportion of 45 or more. That's not unusual then. I expected at about 15%. Or it's not sufficiently unusual for me to get upset about it or think something has changed. Of course, there are other examples we can use. We talk about 60% of registered voters in a district, over 20,000 people are Republicans. If you choose a similar sample of 1,000 registered voters, what's the chance the proportion of registered voters will be between 58 to 62? What's probably the sample contain no more than 550? So it's slightly different. So our assumption's satisfied, and yes, it was taken randomly. Did we sample less than 10% of the population? Yeah, 1,000 is less than 10% of 20,000, and I show that. And of course, this gives me my dependence. Now I need my success failure. I need my NP to be greater than 10 and NQ greater than 10. If I look, well, NP, 1,000 times 0.6, that's 600. And the rest of them then would have to be failure then. 1,000 times 0.4 is 400. So I've got my big enough. Since I have my big enough, I can find my mean, my standard deviation. My mean comes straight from the population. My standard deviation, I use that to find it. Now I can answer my first question. I want to find out about having a 58 to 0.62. So I'm going to find my two z-scores. I'm going to find out and shade my area in the middle. So I look at that first z-score. So my 58, subtract the mean, divide by standard deviation. I get a negative 1.29. And my second z-score, my z-score for the 0.62. 0.62 minus 0.6 divided by 0.0155, and I get 1.29. I have a nice symmetrical shape here. I sketch out my curve, put it inside the TI 83 or 84, put in my values, and I find out that I expect this to happen about 80.29% of the time. So if 60% is the proportion, then yeah, a lot of the time, 80% of the time, that's what I'm going to find. I'll be right in between those two values, about 80%. So let's talk about part B. The probability of a sample proportion containing at most 55% Republican. It's 550 out of 1,000. We know from previous when we've done our condition and our assumptions. So we find our z-score of that 0.55. And we find out that it's negative 3.23. Now if I put this into my normal CDF, if I sketch this out, give myself a little pen. If we sketch this out, so we have that negative 3.23. We're far down here in the tail at this point. And we said no more than, so really we're looking for how much is left over here? Do we expect this? We're pretty far down the tail. So if I do this, is this likely to happen? And I do my normal CDF. That's, if you now convert that to a percentage, that's less than, it's not even 1 out of 1%. It's 6 out of 100. This is tiny. This is not likely to happen. But what if it did happen? What do you think about that? So if I did a sample and I found this, if I had that small percentage, that'd be a highly unusual result. I would definitely not have expected that. I would say maybe my proportion Republican in that county, maybe my original estimate was wrong. That's not how many there are there. It must be a smaller amount. So maybe I'll do another survey. Randomly sample another 1,000 voters, see if I get a similar result a second time. Now at this point, we had a few questions we worked out. Okay, we practiced these. I'll leave this up, pause the video, see if you can answer this, come back, give you the answer. Okay, so if we think about this, records are large in university, indicate 20% of all freshmen are placed on academic probation, random sample of 100. See, I love seeing that word random because it reminds me about my assumptions. I have to assume independence, and a random sample is half of what I need to get there. 100 of this year's freshman class indicated 25% of them were placed on academic probation. The results of the sample, and what do I need to know? So, is it surprising? Is it not surprising? What do we need to know? So, since I'm doing samples, I know I've got to deal with my assumptions. One assumption, I have to deal with independence. Is there independence? Well, it was randomly chosen. Does this follow that it's less than 10% of the population? And yeah, 100 freshmen. As long as there's more than 1,000 freshmen, that seems to indicate it. I do 100 times 10, less than 1,000. And some universities, 1,000 freshmen is an incredibly tiny class. So I'd say yes, I'm going to get my independence. Now, so say, do I have my large enough sample? I'm dealing with a proportion, so I need n times p. And p was given to me as 0.2. So 0.2 times 100, that's 20. So that gives me 20 successes. And nq, so this can be 100 times 0.8, gives me 80. Those are both more than 10. I have a large enough sample. So now I plug those in, find out is this unusual. If I do that, oh, my standard deviation, that means I'm going to need my new standard deviation because standard deviation is samples. So my standard deviation of p hat is going to be the square root of 0.2 times 0.8 divided by my sample size of 100. Let me plug this through. My calculator. I can't get it on the screen all at once. Here we go. So we do this, we would do second square root 0.2 times 0.8 divided by 100. And a standard deviation of 0.04. And we go back down here. So 0.04, we know that's our standard deviation. Okay. Oh, gave it away. But when we have that standard deviation, now we can do our normal CDF. We found C, the difference of 5%, it isn't that extreme. Our standard deviation was 4%. Being off by 5, we're definitely not in an unusual result territory. So number 2, according to manufacturer, the average proportion of red candies in a package is 20%. So 20% of the bag is supposed to be that. 8-ounce package had 250 candies. Find the probability a randomly selected 8-ounce package contains less than 45 candies. So again, we're talking about a sample here. We have a randomly selected 8-ounce package. Actually, no, we don't have a sample here. We just have one package. They tell me right away what we have going on. That, oh, I'm sorry, the package was sampled randomly. Let me make sure here. 10 times 250. I threw some things off. This was supposed to be random selected. This should have been. Oh, yes, because they have all their candies. Okay, that 8-ounce package. Knew I had something here. Sometimes that happens. Read my own work, don't know what I'm doing. That 8-ounce package contains 250 candies. This is my sample, my 250 candies. I knew something was odd. 250 candies, that's my sample. Well, 10 times 250, that's definitely less than all candies. It was randomly selected. 250 times 0.2, that's more than 10. 250 times 0.8, that's greater than 10. So my assumptions, my conditions have been met, so my assumptions are satisfied. So I want to see what did I find. Well, my p-hat, I had 45 out of 250 is 0.18. My standard deviation or standard error, in this case standard deviation, is 0.2 times 0.8 divided by 250, square root it, 0.0253. Well, now I want to find out what's the probability of my having less than 45 candies. That's the same as saying my proportion is less than 0.18. So my z-score of 0.08 minus 0.20 divided by my standard deviation I found is negative 0.7905. And if I do a normal CDF of this, I find out that I have 0.2146, or about 21% of the time. My packages are going to be set up like this. That's not an uncommon event. That's common enough that I'm not upset by it. 21% of all samples will contain less red ones than they claim in the population. So number 3, mathematics department publishes a claim. Minimum of 70% of students enrolling in classes get a final grade of C- or better. Simple random sample of 50 students from the department's classes indicate that only 65% of the students had a C- or better. What is the probability that a sample of this size will have a result that differs from the claimed proportion by more than 5%, above or below? Would that result surprise you? And let's state a conclusion. So pause the video, and before you pause it, think about this. We're dealing with samples. You're going to have to notice your assumptions and then check your conditions. Then see if you'd be surprised by this. So like I said, first thing is check our assumptions. Got a simple random sample, large population, according to this from over a period of time. So I get my n times p, n times q are both over 10. I have my p, I find my new standard deviation for my standard deviation of the samples. So I'm looking for what's the probability that my p-hat would be less than or equal to 0.65, or the probability that my p-hat would be greater than or equal to 0.75. Now remember, from probability, this means we're going to add these two together to find that probability. So my first z-score, I find it, negative 0.772. I do a normal CDF of that, and I find the probability of that being 0.22. I also find, turned out these were symmetrical. So our normal CDF for the other is also going to be 0.22. So if I add those together, what I'm looking at is, no, I'm not surprised. I expected about 44% of the time I'm going to be that far, because remember, it said in either direction. 0.22 on the low end, 0.22 on the high end. Go back so we can see that. I expect that. So overall, that or, adding those together, about 44% of the time we're going to be off by that much. So I'm not surprised. Let's try one more. I guess simple random sample, size 200. Well, not one more, but another one. Taken from a population of 1,000, professional organization. What's the probability that this sample will produce a result of 10% or less favoring arrays when it's known that 3.5% of the population favors arrays? Well, pause it, think, check your assumptions. Oh, wait, my assumptions. One of my assumptions is about independence. I can't sample more than 10% of my population. I've sampled far too many, because 10 times 200 is 2,000. I've sampled far too much of my population. I can't use this distribution. It's not going to be normally distributed. So I already know I'm done. There's no more work to be done. So always check your assumptions. Might save yourself a lot of time. So now we have another one. We need to find the size with simple random sample needed so that the probability that its proportion differs from the population by more than 2% is 0.1. And we're going to assume the population proportion is 0.63. So what we're saying is, what z-score is going to give me 5% in the tails? Because if I'm going to be differ by more than 2% is 0.1, well, that's in either direction, just like in our mathematics department. So 0.05 on one side, 0.05 in the other. I find my z-scores for that. Well, if I do that, my z-score is 1.645. They've given me the values. I'm looking to try and solve for n. I'm using that algebraic manipulation here. I'm just moving things around. Next thing I can do, I want to get that square root of n off on by itself. I'm going to take a bit of manipulation. Now I have to divide by that 0.02, multiply by 0.4828. But now I solve, I have the square root of n is 39.71. So I square it. Now I've got a sample size of 1,576.93. But remember, we're dealing with samples. Anytime we're dealing with samples, sample sizes have to round up. So we're going to have 1,577. And this is the same thing we're going to see in chapter 19. Always have to round up our sample sizes. Well, that finished it up. Last thing we had was some homework, completing the handout if you weren't quite on the stage 3 questions. And these are the questions we did for the homework. So good luck. Look forward to seeing you in class.